All right, good morning, everyone. We're going to go ahead and get started with VC Ag today. Thank you for joining us. This will be recorded, so if you find this useful and you need to go back and look at something else, you can go to the recordings at the link that's listed down at the bottom. However, today we have two great speakers with us to help us understand how to read our soil test reports. We have Parikh McGorry from Waypoint Analytical and Dr. Rory McGuire, which is our soil extension specialist at Virginia Tech. So thank you, gentlemen, for joining us. Just some housekeeping rules. Please stay muted while the presenters are speaking. We will give time at the end of the presentation for questions when you can unmute yourself. If you have questions throughout and you just want to get them out and ask the question, you can put those into the chat at any time. So the chat can be found down at the bottom of your screen. And again, just keep yourself muted throughout. And if by chance we have someone like a Zoom bomber, we will have to end the meeting and we will get back up with the presenters and record something for you so that you can still get the content. But again, thank you to our speakers and thank you for joining us. So we're going to start with Parikh. So Parikh, if you could join or share your screen.
Yeah, I'm clicking on it now, but it says this will stop others sharing the screen. I'm going to hit yes.
Yes.
Can you see it?
We can see your screen, so you just need to go.
Okay. Well, Thank you very much for the invitation to come talk today. Like I said, if we can hold our questions at the end, that would be great. And like I said, I'm going to start off pretty much going over each of the different parameters on a Waypoint Analytical soil test report. I know Dr. McGuire is going to talk on the Virginia Tech afterwards. So we're going to start with the one that I probably get the most questions about, and the one that probably gets most understood is going to be soil pH and buffer pH. And for most people now in the ag world, pretty much everyone should know the effects of basically pH on nutrient availability. So when we get a soil test report back, we're going to see a number on it. And ideally, what we're going to be shooting for is to have a soil pH somewhere between 6 and 7. With Waypoint Analytical, we shoot for a 6.2. And if you have some legumes out there, we may shoot for a 6.5, but that just really depends on your preference. But ideally, like I said, you should be shooting somewhere between 6 and 7 because that maximizes nutrient availability. Some of the other effects that soil pH has on is basically nodulation on the plants. Basically on the left, we have basically the soil pH that was measured and then the count of the nodules on the right. So you can see how important soil pH is as far as on soybean nodulation. And generally speaking, as we increase the soil pH from 4 to 5 to 6.5, we're doubling the amount of nodulations on the plant, which is obviously going to grow more biomass and hopefully lead to more flowering and more pod development and bigger beans at the end of the day and higher yield. So you can see clearly here the effects of soil pH just on encouraging nodulation on soybean plants. One thing that we really don't talk a lot about is what happens when we get down to low pHs, particularly less than 5.5. And on the graph or the figure on the left-hand side, you'll see as the pH decreases below 5.5, we get an increase in basically aluminum concentration in the soil, particularly soluble aluminum, which basically is very toxic to the roots. On the bottom right-hand picture, you'll see what happens with a pH of 4 with aluminum at 15 ppm. You can see that we basically no roots at all. And then as you can see at a pH of 5.1 that had a ton of lime applied to it, basically in less than 2 ppm of exchangeable aluminum, you can see how healthy the roots are. So ideally, if your pH is low, we don't want it to go less than 5.5 because that's when we start seeing really issues with aluminum toxicity. And back in the day when North Carolina Division of Agriculture came out with these target pHs, we used to just lime to a 5.5. It wasn't later on until we seen the benefits of nutrient availability that we started increasing the target pH to 6. The one other thing, when pHs go down really low, particularly down into the low 5s and particularly into the high 4s, is we can induce manganese toxicity. So this basically means if you have large concentration of manganese in the soil, manganese becomes more soluble in the soil, which basically can lead to toxic levels in the plant. So that's something to be wary of as well. So when you get a soil pH result back, what are we actually measuring? Basically what we're doing, there are two types of acidity in the soil. We have active acidity and reserve acidity. And basically active acidity, what's in the soil solution. So that's what actually the soil pH, that's what we're measuring when we get a soil pH number back, is actually what the soil solution, hydrogen and aluminum are in that solution. So we were going to make a lime recommendation off just the soil pH. It would only take about ½ pound of lime per acre to neutralize this here. So I know most people in the audience will know that we put a lot more than ½ pound of lime out here. So basically the question I have then is sorry, I'm skipping ahead. So what basically the idea of the soil pH is basically all it does for us is to trigger how much lime or sulfur to apply. So basically if your pH is less than 6.2, then we know we need to apply lime. If your pH is greater than 6.8, it triggers how much sulfur you need to apply. It does not tell you the quantity of lime or sulfur to apply. The other thing to remember by soil pH is it's not a number that stays pretty much consistent through the season. As you can see here, this was soil samples taken, 32 composite samples taken over a time period starting in the summer and going over a fall, winter, spring, summer, and fall back in 1972 in Arkansas. And you can see the pH started at 5.4. During the summer, it dropped to a 5.15 and then rebounded in the fall again to 5.6. And there were no lime put on at any time during this study, by the way. It then stayed constant over fall and winter, increased a little bit in spring, and then you can see basically it dropped right back down to a 5.10 in the summer again before rebounding back up again to the fall to a 5.7. So the take-home message I want to give you on this here is that when you take a soil pH, the numbers are not going to stay consistent from one year to another, and it's going to go up and down depending on what your fertility practices are and what your cropping rotation is. So what is the reason for some of these pH seasonal fluctuations? One is the main one is going to be the application of N fertilizers, which produces hydrogen ions. The second one is basically when we put a crop system in the soil, it produces carbon dioxide, which forms carbonic acid. And then we end up, when you grow a crop also, you get an uptake of a lot of the calcium, magnesium, base cations, which again is going to reduce the pH. And the main one I see is going to be the fertilizer salt depressors. So basically when you put out fertilizers as well as the hydrogen, also accumulation of salts is also going to naturally decrease the pH readings. When we see the increases in the fall and in the winter, we basically see a leaching out of the salts, and we also see a release of the calcium, magnesium back into the soil solution, which buffers it and basically causes the pH to go back up again. So this was a study done in University of Georgia by Dr. Kissel, and he basically showed by taking a soil sample and basically by adding salt concentrations to this, we can drop the soil pH from a 6.0 to basically down to a 5.2 and even down further by just by adding salt to it to a 4.8. And if you can see here an arrow in the middle of the screen, basically that's equivalent to putting out 120 pounds of K2O plus 150 pounds of nitrogen. So if you put out 100, that's normally a fertilizer practice that you put out for an average of 150 bushel corn crop. And you can see here by just putting out that fertilizer in the soil, you can get basically a significant drop in soil pH, basically from a 6 down to a 5.3. So if you take a soil sample in the spring and the pH comes back good and you take it later on in the season after we put our fertilizer out, don't be surprised that your pH has come back about a ½ point lower than you would normally see earlier on in the season, like in the spring. The other thing I would like to point out is generally on average, when we take soil samples after a corn crop, we normally see our pHs run about 0.3 lower, especially on a dry season, versus if we have a really wet season, like if we take soil samples in the spring, generally we see soil pHs run slightly higher, about 0.3 in the spring. So they are going to be variation between what the pH will be after a corn crop in the fall versus what actually the soil pH will be in the spring after it gets a rainfall and that, because it will leach out some of them salts and the pH will actually increase from it. So please be aware that sampling in the fall and the spring are going to lead to slightly different pHs. So just moving on to buffer pH. This is probably the most least understood parameter that gets really confused in soil test reports. So hopefully I can do a better job of explaining it. Like I talked there along with soil pH, it measures the active acidity in the soil solution. And it only takes about ½ pound to neutralize. Well, we need to figure out why do we put on a ton of lime? Well, when we put out the lime, we actually need to measure the reserve acidity, and this is actually determines how much lime we need to put out. And this is where the greatest amount of total acidity is going to occur is in the residual and exchangeable forms. So basically the buffer pH tells us how much lime you need to put out. The soil pH tells us if we need to put out lime or not. The buffer pH tells us how much lime we need to put out. So here's an example of why we need a buffer pH. On the top sample, you can see here the 5.5. We have a lower sample right below it that has a pH of a 5.5. But if you go down here, you can see there needs two different lime contents. On the first sample, it's 1.3 tons. On the second sample is about 0.8 tons. And you're like, well, they both have the same soil pH. Why we need different lime recommendations? And this is because of the buffer index. The lower the buffer index number, the more lime we need to apply. So basically at a 6.85, this is higher than the 6.7.4. So here you need less lime than the lower buffer pH. Pretty simple. So I've seen times, depending on the soil, we can have the same soil pH, but we can have completely different lime recommendations, and that is quite normal. So the other way to understand this is basically if you have two tires and you fill them up to 30 PSI, which tire needs the more air? And obviously if it's a tractor tire, you're going to need more basically air to fill the tractor tire to 30 PSI than the car tire. And that's the same as more recidivity. Some soils have more reserve acidity than others. And how we measure this is through basically measuring the buffer pH. So how do we go about making lime recommendations? It's pretty easy. You basically will get the buffer pH on the soil test report is a 6.7 here. You go to the lime recommendation table, you go across and you basically see that we recommend 1.5 tons. It's pretty straightforward. If we had a 6.3, you would go across here to your target pH and you're going to get a 6.2. The main thing is you need to know what buffer test that each lab is running. Virginia Tech runs Mehlich, we run SMP. So if you're going to do your own lime recommendations and you send the samples to Waypoint, you need to make sure that you basically are looking at an SMP buffer test and not another lime table. So the question I get commonly about difference in lime is when to apply dolomitic versus calcitic limestone. If your magnesium soil test is low, very low, basically I recommend applying dolomitic. If your calcium soil test is very low or low and your magnesium is very high, then I would apply calcitic. So my rule of thumb is if magnesium is high or very high, apply calcitic. If your magnesium's low, very low, or medium, I'd go ahead and apply dolomitic limestone. It's also important that people call about, well, I put lime out 6 months ago, I don't see any difference. It takes roughly about 12 months to 18 months for the lime to fully react. So if you put lime out in the fall and you take a sample 3 months later, don't expect the pH up to be very high. Mostly we see about 0.2 to 0.3 change after 6 months. So just remember that it takes over 12 to 18 months for a ton of lime to fully react and get to the maximum potential of that lime application. Moving on to cation exchange. This is something we really can't change a lot. No-till practice will increase the organic content, and if we manage our pHs right, we will see an slight increase in CEC. But the main role of the CEC is basically its ability to hold your base cations, which is basically your calcium, magnesium, potassium, and then also some of your acidifying cations, which is going to be aluminum and hydrogen. But it's generally mainly you're going to find your calcium, magnesium, potassium on this. In Virginia, we range from around 3 to 15 milliequivalents, depending on how much clay is in the soil. And generally, the rule of thumb is obviously the higher the clay content, the higher the CEC, the lower the clay content, the lower the CEC. So generally, we will see basically a CEC of less than 6 if it's sandy, and if we have really higher textured or heavier textured soil with loads of clay in it, we're probably going to get to a CEC around 14. When it comes to organic matter, again, this is something that we can increase through no-till practices. We're not going to go out and incorporate a bunch of compost into an acre or two. And pretty much is putting on no-till cover crops is the best way to improve this here. Generally in Virginia, we range somewhere between 1.5 to 5% organic matter. The one thing that organic matter will indicate is generally where you see higher organic matter contents. It normally tells us that the soil stays a little bit wetter and cooler. Sometimes organic matter content is used as a nitrogen recommendation factor. I'm not a big fan of this, but it is getting more and more prevalent where we're basically using organic matter as a factor into making some of the nitrogen recommendations on some of our crops. And a lot of research has been done in this area. Moving on to nutrient levels, pretty much what we have is we have a rating system. And basically it's called very low, medium, high, and very high. And basically that tells you what the probability of us getting a nutrient response to that rating. So if you're very low, you're probably going to have the 75 to 100% going to get a response to that. If you're in the medium, you're probably going to have 50%. If you're high, you probably have a 25%. And if you're very high, you're highly unlikely to get a response by applying a fertilizer when it's rated that high. So the very high does not tell you that it's toxic. It just merely tells you that you're not going to get a response by applying more fertilizer because there's so much nutrients of that particular element in the soil at the moment. Now moving on to base cation saturations. So this is a conflict of interest because a lot of people like to try to base fertility recommendations in this. And this is basically called BCSR. And basically back in 1945, Dr. Baer and co-workers in New Jersey basically came up with this idea of having ideal soil ratios. And basically you have, they came up with a ratio of calcium having 65% base saturation, magnesium 10, potassium 5, and hydrogen in about 20. And they thought like having a calcium to magnesium potassium ratio would be 13 to 2 to 1. And they found out that if you got in these ranges that you can maximize the yield of your crop. Some years later, 1959 with Graham and 1981 with Baker, basically adjusted. Instead of having a statutory number, they basically put a range in. So instead of having 65, they went to 65 to 85, 6 to 12, and 2 to 5 for potassium. And then it got, like I said, redeveloped again and basically went to 60 to 80. And down below that, there's some ratios. You can see that basically the ideal ratio for calcium and magnesium can be 6.5 to 1, 5.1 to 14, or 3.1 to 8.1, depending on whose interpretation you want to have. So this is the idea, is that if we get within these ranges, we'll maximize our yield of our crop. So here's a report that has the ideal base saturation ratios on it down at the bottom here. And each sample that we have here matches the ideal ratios. And as you can see here, we have a sample called LE and RE. And as you can see, both have the same pH. And the question I would ask if I was in front of an audience would be basically which basically soil would you want to grow a corn crop in? And like I said, the one that you want to be growing the corn crop in is the top one, which is the LE. You can see again, both of these have the ideal base saturation ratio. But this one on the top has 190 ppm potassium, 120 magnesium, and 1200 basically calcium. You are not growing a corn crop on 50 parts per million potassium, 30 magnesium, and 300 of calcium. So you can see here, you can have two soils which have the exact base saturation that you want, but they contain very different nutrient concentrations. And that's the take-home message I wanted to get delivered across here, is that you got to be looking at just not the base saturations, but you also need to be looking at the concentration of these nutrients in the soil, because people get tied into one, you're going to lose focus the other, and you're not going to end up putting out the correct fertilizer you need for your crop. So here's another example with the ideal ratio. Basically, the ideal ratio for calcium, magnesium, potassium was 13 to 2 to 1, which is in both of these samples. It perfectly add up, but you can see the difference of concentrations in calcium, magnesium 60 to 30 and 98 to 49. Again, you will not grow a corn crop in this. You will in this soil, but again, they match the ideal ratio every single time. So we do not want to just look at the base saturation ratios and say, my fertility is good, I don't need to apply any more fertilizer. And then this is some of the actual research that was done. They basically came up with different ratios: a 2 to 1 the calcium, magnesium, 3 to 1, 4 to 1, 5 to 1, and 8 to 1. And this is the ratios that actually occurred in the plants. And basically, this is the base saturation of calcium, magnesium, which is pretty good. But the main take-home message here is going from a 2 to 1 calcium and magnesium to a 5 to 1, you didn't get any significant differences in yield. So you went from a 3.31 tons of alfalfa to 3.5. And so by increasing your calcium magnesium ratio, you didn't really get that benefit, and meeting their criteria didn't increase your yield that much. So the main thing that I would say is, while Dr. Albrecht was highly respected as a soil scientist, when he applied the dolomitic limestone to get the different base saturations, he didn't take into account that this has actually improved the soil, they increased the soil pH. So he put the response down to basically increasing the base saturations, but he probably got more benefits of increasing the pH than what he actually did with basically putting out the lime and increasing the base saturation levels. So the take-home message is we got to look at both of them. And the way I look at this here is we can have a healthy, balanced diet, but we can starve ourselves to death. So I can eat that right amount of fats, meats, veggies, and rice. If I only eat 500 calories a day, I'm not going to survive. And that's like a corn crop. we have to have things in the correct balance, and we also have to have things in the right concentration. So I need to eat 2,500 calories a day, and I need to eat the right balance of diet to be able to grow big and healthy. So that's pretty much all I have to talk about on the soil test, but they are one thing I wanted to say that people say, well, why does my results vary from year to year and don't match exactly the same? Remember that in a 5 acre, 6-inch furrow, they're basically 10 million pounds of soil. We get 2 pounds of that and we test only half an ounce. So please understand that your soil is very variable out there. You are going to see differences in results, even if you go back to nearly the same spot. The research has shown if you take a sample 6 inches from each other, the results will vary. But it's amazing that we only test half an ounce of soil in basically 10 million pounds of soil, and that's what your whole fertility program is based on. And then the last two things is, I know it's wheat season right now at the moment. Here we have a slide of basically a really healthy green field here. On the right here, we basically have a yellow wheat field. And here's the tissue sample from the poor wheat field. As you're probably wondering, it looks really healthy and we don't need to apply any nutrients. But please make sure when you get these tissue reports back at this time of the year that we're looking at the nitrogen to sulfur ratio. We should be less than 18:1. Right now, that field here on the right-hand side was at 22.9. So please, when you're putting that nitrogen, don't forget about putting some sulfur in there to balance off the nitrogen to sulfur ratio, and particularly when you're taking tissue samples at that time of the year. And at that, I'm pretty much done, Laura, and I'll hand it back to you.
All right, thank you. All right. Does anyone have any questions specifically for Parikh? All right, hearing none. Thank you so much. Please hang on. Maybe there'll be some other questions toward the end. All right, you ready, Dr. McGuire?
Sure, let me start sharing. So hopefully you can all see this.
Yes, we're all good. Thank you.
Okay, hello everybody. I was asked to present on the same subject as Parikh today, so it's not surprising that there's going to be some overlap, but in many ways that's good because it emphasizes some of the most important parts of soil testing. So some questions: how precise is soil testing? If you submit sometimes we get questions about I submitted a sample last year versus this year and the numbers are a little bit different even though I didn't fertilize. And as Parikh was talking about, there are different aspects of soil testing and the biggest error is associated with sampling. So you really need to take that representative sample from the whole field. As he was saying, you take half an ounce is what we analyze, but there are about 2 million pounds per acre. So you can obviously see that there's a large potential for error in the sampling. We're very good at the analysis and we're very consistent with the interpretation of the soil analysis into a fertilizer recommendation. But I can't overemphasize the importance of taking a representative sample. Soil fertility changes across a field. There are low spots, there are sandy areas that are going to be testing a little bit different. I mean, you can tell this in many fields just by looking at the yield, how it varies across fields. So it's very important. And you also get soil fertility changing with depth. So if you take a deeper sample, generally you get lower numbers because nutrients like phosphorus tend to accumulate near the soil surface unless you're tilling them in. How does weather impact soil testing? Or I covered the pH, but when you look at the primary nutrients, everybody knows nitrogen leaches, but most of the nitrogen's bound up in the organic matter. We don't tend to analyze nitrogen other than the pre-sidedress nitrate test. The nitrogen recommendation is based on the crop to be grown and your realistic yield expectation or soil type. And your soil type, we have different productivity groups for your yield expectation. Phosphorus, we held very strongly by the soil. That's why it accumulates near the soil surface. In no-till, you can have it twice as high in the top inches below that, or even more. Potassium, again, held very strongly by the soil by the cation exchange capacity. Cation exchange capacity is the negative charge of the soil, and potassium has a positive charge, so it's held fairly strongly by the soil. So when you look at a typical soil test report from, this is one of the Virginia Tech ones, the top bar there is all information that's provided when you submit the sample. So it's where the sample came from, what crops to be grown. The crop to be grown is very important. It provides the target pH that we're trying to lime to. It also provides information for the nitrogen recommendation. And this SMU is the soil management unit. Depending on your soil series, it'll provide you realistic yield, or if a farmer actually keeps his own yields, he can provide that yield estimate. Some farmers are better than others. Some farmers will be getting higher yields on the same soil type, but a lot of farmers still use this soil series and the productivity group there. When you look at the main nutrients, nitrogen, phosphorus, potassium, again, we don't measure nitrogen in the soil. It's based on the realistic yield expectations. Phosphorus and potassium, we measure the concentrations in the soil. We measure it in parts per million, and then with 2 million pounds per acre in a furrow slice, we multiply by 2 to convert it to pounds per acre. So the phosphorus there, 9 pounds per acre, and that's just the plant available component. There's a lot of reserve phosphorus in the soil that's not plant available immediately. So with our extractants, we only measure the proportion of phosphorus that's available in the soil. So you can see phosphorus and potassium, they're two of the major soils, and just as previous speaker, we break that down into low, medium, high, and very high. So you can see the phosphorus there is very low, the potassium is in the medium category. In this next series, you've got the major cations, calcium and magnesium, and those are corrected by lime if necessary. The previous speaker talked about dolomitic limestone where your magnesium is deficient. We've also got several other micronutrients there, the zinc, the manganese, etc., and those can be corrected with foliar fertilizers. We get lots of questions about the soil pH. When I started at Virginia Tech 14 years ago, we just implemented the buffer index. Initially, it was called the buffer pH because it is a pH, and it was confusing people that we had a soil pH and the buffer pH. So the soil pH is actually the pH of the soil. The buffer pH, now called the buffer index, we add a salty solution, a buffer solution that starts at a pH of 6.6. It knocks the reserve acidity into solution, and then depending on how far the pH drops below that initial 6.6, we know how much reserve acidity there is to apply lime. So the soil pH tells you, or tells us, where the soil is at currently, and the buffer index is only used to determine how much lime needs to be added to change the pH. So the cation exchange capacity, the estimated CEC, the CEC itself is not used in any recommendations, but generally the higher the better. We've had some questions from a lot of clientele on why are our CECs so low. People like to go on the internet and look up information, and they find CECs up around 50, and our CECs rarely get much above 10. And that's because the soils here in Virginia were never glaciated. So because of that, our soils are older than up in the Midwest, where the soils were stripped by glaciers. So most of the clay in Virginia is kaolinite. So even where we have clay soils, the kaolinite has a very low CEC compared to some of the clays up in the Midwest. So be careful when you're looking at recommendations for CEC, because our soils are a little bit different than in other states. So be careful where you're getting your information from. But the cation exchange capacity, the negative charge of a soil, it's either covered with acidity or your base cations, your calcium, magnesium, and so on. So you can see the acidity plus the base saturation add up to 100. And then if they're the ratio of calcium, magnesium, potassium, and these ratios aren't used in our recommendations. As the previous speaker talked about, You can see the ratio there, but it's not used. We don't use or subscribe to the base cation saturation ratio. Because on soils with low cation exchange capacity, you can end up with potassium deficiencies. So we subscribe to the sufficiency approach and making sure that you have enough pounds per acre of your nutrients to get a good yield. We don't run the soluble salts or organic matter routinely. You can ask for these. Soluble salts isn't used much, but occasionally it's used by the greenhouse industry to make sure that water that they're recycling isn't causing salt problems. You can measure the organic matter, but again, it's not used in the nutrient recommendations. Generally, more organic matter is better, but it doesn't change very much year over year. More organic matter, soils with more organic matter tend to have higher yields and better structure and so on, but it doesn't change year over year. And still, for our nitrogen recommendations, Dr. Wade Thomason has been doing a lot of research on nitrogen rates, and that 1 pound of nitrogen per bushel realistic yield expectation is still the best way to go. We're doing a lot of research in terms of carbon dioxide bursts and other things to link organic matter to nitrogen, but that 1 pound of nitrogen per bushel corn is still the best way to get a nitrogen recommendation rather than relying on organic matter. So in terms of understanding a soil test report, this bit at the bottom is generally the part that most people look at. How much lime do I need to apply to keep my soil pH correct? And how much fertilizer do I need? And in terms of type of lime, if your magnesium is low, we can tell you to apply dolomitic limestone to build up your soil magnesium. But here it says AG, which is ag lime. Just it means whatever's cheaper. It doesn't matter if you apply a calcitic limestone, which is calcium carbonate, or dolomitic lime, which is still primarily calcium carbonate, but it has some magnesium carbonate in there. It doesn't matter which you apply, just whatever's cheapest available. So that's what the AG ag lime means. So, and then in terms of the main fertilizer, nitrogen, phosphorus, potassium, you can see the pounds per acre recommended at the bottom. Again, nitrogen is based on the crop to be grown and the realistic yield expectation. And the phosphorus and potassium are based on the concentration in the soil and how much we need to grow a good crop. So when the original work was done, most of the calibration work for soil tests was done in the 70s. Soil testing is actually fairly new. There wasn't much in the way of soil testing going on anywhere in the world before about the Second World War. Most of the calibrations and development of the soil tests were done in the 60s and 70s. Mehlich 1 was developed in about 1954, Mehlich 3 in about 1984. So they're fairly new still. But this is what a response calibration curve look like. So when you're in the very low or low category, you're definitely going to get a yield response. Whereas you move up to medium, you've got to remember that across a field, nutrient status changes. And again, we're only analyzing about half an ounce of soil under 2 million pounds per acre. So there's going to be some variability. So there is some insurance built into the recommendation procedures to make sure that you're going to have enough of the nutrient across the entire field. So we don't just use that critical soil test level where we're 100% sure we're going to get a yield response. We have a little bit of insurance to make sure that any load testing areas across the field also get nutrient recommendations. So again, phosphorus, low, critical soil test of 12 pounds per acre, but we don't, and then we step down the phosphorus recommendations as we get above that, but we don't go to zero till about 55 parts per million for most crops. And in Virginia, the sandy soils on the coastal plain always cause us headaches. The sandy soils near the surface often have clay layers underneath. So when you take a routine soil sample to up to 6 inches, maybe a foot down in the soil, there's a clay layer that'll hold a lot of potassium that isn't picked up in that soil test. So that's why even though in low potassium testing soils in the coastal plains, sometimes you don't see a potassium deficiency because there is that clay layer that the roots get down to. And that clay layer also tends to hold a lot of sulfur. So obviously low testing soil is going to need more phosphorus and potassium to provide enough for the crop to grow in a medium high. So you can see there the phosphorus, you're 80 to 120 pounds per acre at low, and then as you go up to medium, the recommendation drops, and the high, it drops again. And there's a range there because there is, for each category, there's a negative, minus and positive. So there's medium minus, medium positive. So depending on that, we have a recommendation of pounds per acre. Whereas nitrogen, again, we do not measure nitrogen in soil. It's based solely on the crop to be grown. And for corn, it's 1 pound of nitrogen per bushel. Lime recommendation is the thing we get most questions on. So it's the crop code sets the target pH. Something like blueberries needs a low pH. For most crops, we have a target pH of 6.2. For things like alfalfa, we go up to 6.5. So the water pH, we measure the pH with water, and that tells us where we are. And then again, to emphasize what the previous speaker was talking about, we use a buffer solution to measure the reserve acidity in the soil. And that tells us how much lime we need to apply to change the pH. More clay, more organic matter lead to higher cation exchange capacity, lead to more exchangeable acidity or reserve acidity. Most people understand that a sandy soil is going to need less lime to change the pH than a clay soil. So just a visual representation of this. So both of these red blocks represent soils. So the top one is a low cation exchange capacity soil. The one at the bottom is a high cation exchange capacity soil. Let me see if I can put on a laser pointer. Okay, so this is a low cation exchange capacity soil. This one is a high cation exchange capacity soil. Each of these little dashed lines represents a negative charge. So you can see in both of them, we've got our potassium, calcium, and so these are our base cations. And then this H+, that's acidity. That's the reserve acidity that's sticking on the cation exchange capacity and isn't measured when you just do a pH measurement in water. But our buffer pH does measure this. So you can see both the low cation exchange capacity soil and this high cation exchange capacity soil. The water pH comes out at 5.5 because half saturated with acidity, half with cations. But when we have a buffer solution, what that buffer solution does, it's a salty solution, it'll kick all of this reserve acidity into solution where it'll be measured. So our buffer pH, the Mehlich one, again, Waypoint uses the SMP, so they start at a different pH level. Our buffer pH starts at 6.6, and anything below that shows that we're kicking reserve acidity into solution. So because of that, this one has low cation exchange capacity, low reserve acidity. It kicks the buffer pH from 6.6 down to 6.25. This soil with a high cation exchange capacity obviously has a lot more reserve acidity. So it kicks the buffer pH all the way down to 6.1. So because of this soil, even though both soils start with a pH of 5.5, this one on the bottom needs more lime to change the pH. So the lime recommendation for the one at the top is 3/4 of a ton per acre. The one at the bottom here has a lime recommendation of 1.5 tons per acre. So even though they start at the same pH, we have different lime recommendations, and that's based completely on the buffer pH, which measures the reserve acidity of the soil. And that's what we get a lot of questions about. So again, here's how our lime recommendations are made. So our buffer solution starts at 6.6, and if after mixing it with the soil, if it comes out at 6.6, there's no reserve acidity, we don't need any lime. And then as the buffer pH, call the buffer index on our soil test reports to avoid confusion. As that buffer index drops, or the buffer pH drops, our lime recommendations go up. So we have different target pHs. So you can look at, there's a table. We give you the tons of lime on the soil test report, but this is where it comes from. And you can look at our recommendations guidebook. We've got a target pH, and combined with the buffer pH, that gives us a lime recommendation. Again, I always like to put a a shout out to people that submit good soil samples, and also request people not submit bad soil samples. So these are our soil testing boxes that we receive in the lab. The one on the left here is what we like to see. The one in the middle here, we're only going to measure about half an ounce of soil. Submitting more soil isn't going to increase the quality of your soil sample. So don't pack the soil into the soil boxes. We need to dry it. And when you pack it in, it makes it hard to get out. You can soil test at any time of the year, but please don't submit soil samples like this. This is one that was a very wet clay. The first thing we do when we receive soil samples is dry them out. So when we receive very wet clay samples like this and we dry them out in an oven, we end up with bricks. So it makes it very hard to analyze. So please submit soil samples that look like this. They're easy to dry out, and there's a fill line. You don't need to exceed that fill line. Again, the biggest source of error in soil testing is the soil sampling, because you send us about half a pound of soil, and it represents 2 million pounds per acre, or in a 10-acre field, that's 20 million pounds. So it's very important to walk or drive your four-wheel across that entire area, take multiple subsamples, mix them together in a bucket, and submit one representative sample. If you give us a good soil sample, we'll give you a good soil test recommendation, a good fertilizer recommendation. If you send us a bad soil sample, we'll give you a bad recommendation, and it's all down to how you collect the sample. So soil test strategy is very simple. Take a representative soil sample. Very important to get that representative sample. Can't overestimate or overemphasize the importance. And then the second part, obviously, is follow the soil test recommendations. People ask me about nutrient management, and is nutrient management difficult? But these are the two basic steps. Take a soil test and then follow the soil test recommendation. And I think that's me.
Great, thank you so much. All right. At this time, you can unmute yourselves and ask any questions that you may have of either of our speakers. I am not seeing any questions in the chat. All right, anyone have any questions? Guarantee you, if you have the question, someone else has that same question. So don't hesitate. Go ahead and ask.
Yes, I have a question. So if I'm not sure about what I actually want to grow and I want to submit a soil sample for like different, like maybe fruits, crops, nuts or something. So how do I do that on the soil sample? How do I just indicate no specific crop at that time?
It's impossible for us to give a recommendation for something like that, because what's to be grown is an important part, especially for something like nitrogen. I mean, nitrogen for a tree, we don't recommend nitrogen. For corn, we're going to recommend a lot of nitrogen. If you could, we have general things like, so if you pick something like a vegetable garden, we can do general recommendations for things like that. But if you can have a general idea, I would guess something that's closest to what you think you're going to use the land for.
Okay, thank you.
All right. Any last minute questions?
Well, there's a question in the chat box about talk a little bit about water quality and fertilizer recommendations. And there is some insurance fertility in our recommendations to make sure that the crop has enough across the entire area. But you don't get into water quality problems until you get way above the recommended nutrient concentrations. For example, with phosphorus, we stopped recommending phosphorus fertilizer at about 55 parts per million, But when I look at the soil samples that come into Virginia Tech, they can range anywhere from about 5 parts per million to over 500. So it's when you get well above nutrient requirements for crop growth that you start to get into water quality problems. So you don't need to choose between having a good crop and having good water quality. Water quality problems occur when you have too much, way above recommended levels of nutrients. And those high soil test phosphorus levels are due to things like excess manure applications in history. We actually see homeowners way over fertilize a lot because a bag of fertilizer to them doesn't cost a lot of money. So they might buy a bag of 10, 10, 10 every year and put it in their yard. So we actually see homeowners do a very poor job relative to farmers, where fertilizer is a big input cost. But again, you don't need to choose between having good crops and good water quality. Nutrient management is all about following your fertilizer recommendations and not over applying. If you over apply fertilizers, you're not going to get a better looking crops, but you could damage water quality.
Rory, I have one for you. Can you explain to people what happens when they put too much lime down? I had a recent case here where a person put 7 tons to the acre down on his property.
Yeah, you can run into micronutrient deficiencies, zinc and manganese deficiencies. So you don't want to get your soil pH too high. Yeah, because you can start to see micronutrient deficiencies.
Yeah, one comment I will add to that there, 7 tons is abnormal in the ag world, but if you take somewhere like Stafford County that has acid producing soil, 7 tons of lime would be a normal recommendation. So there are cases across the state of Virginia where we have acid producing soils, like in Stafford County, that will require a specific soil test. So if you get a pH below, and Rory can correct me on that, is it below 4 or 3, Rory, that Dr. Lee Daniels recommend, where you would put out a large quantity of lime and needs its own specialized testing?
Yes, for most agricultural settings, we don't recommend more than about 2 tons, at one application. Yeah. As Parag was talking about, we do have acid sulfate soils. We find it a lot around road cuts or home home construction, where they dig up these sulfur bearing rocks. So the subsoils have a lot of sulfur in them, and as soon as they're exposed to air, they get extremely acidic. So yeah, Dr. Lee Daniels here at Virginia Tech runs specific samples for that, and you can get very high lime applications. But for most agricultural or home settings, you don't need more than about 2 tons at one application. And if you get the soil test much above 7, you're going to start running into some micronutrient deficiencies. And you can correct that with sulfur applications to bring this soil pH back down.
Okay, well, thank you. There's some great questions. I'm sure everyone was thinking those questions, even though they didn't know they were thinking those questions. So thank you guys for asking.
There is one more in the question there about submitting multiple samples if you don't know what to grow. But looks like Scott Ryder responded. Yeah, we do have our recommendations guidebook. So if you submit one sample and you find the nutrient status or pH and buffer index of the soil, you can go to our recommendations guidebook and look up the fertility recommendations for different crops. Our recommendations guidebook is available on the soil test website.
If anyone does have a link to that, and you can put it in the chat for us, I don't have it pulled up. But if not, I will definitely include it with the recording of the session so that people have that as a resource, because it's a great one. All right, well, thank you all for attending today. And I'd like to thank the team of agents who helped put this session together. We have Stephanie Romelchek, we have Trent Jones, we have our normal host of the day, Robbie Longest, and Mike Broadus, and Frank Long, and then myself, Laura Maxine in Hanover County. So thank you again, speakers, for joining us. And the way that we pick and select the topics that we go through at VCAG today is we use the evaluation. So please fill out the evaluation and let us know how we're doing. If there's a topic that you would like more information on, that is the place to put it. And you will see it on an upcoming VCAG today. So speaking of which, the next one that we're going to have is in 2 weeks. So we've moved from a weekly VCAG today to every 2 weeks. The next one is March 25th, and we're going to be talking about preparing for strawberry harvest with Jayesh. So hope to see you then. And I think I have covered everything. I really appreciate Robbie doing this each week, so I don't have to remember everything. So we're truly missing him today. All right, thank you guys. And hope to see you on the 25th if you have strawberries.